Hey everyone, welcome to this Finals Prep Explainer. Today, we're literally putting on our data center consultant hats, and we are going to absolutely crush the math behind server virtualization. If you've got an upcoming exam on green computing, or you just want to master the actual numbers behind data center energy savings, you are definitely in the right place. Grab your scratch pad because we're jumping right into it. Here's our game plan for today. 1. The core problem. 2. Consolidation math. 3. Facility math. 4. Analytical scenarios. And finally 5. A concept quiz. Let's get to work. Section 1. The core problem. Okay, before we can fix the math, we really need to understand exactly why these legacy data centers are just bleeding energy. Take a look at this. It beautifully, or maybe horribly, illustrates the sheer scale of server sprawl. In a traditional, non-virtualized environment, the standard rule was one application per physical server. Because of that, legacy servers sit at a miserable 10 to 15% CPU utilization. That means 85% of their compute capability is entirely wasted, yet they're still gulping down massive amounts of power just to stay awake. It's literally an energy efficiency disaster.
So how do we fix it? We use virtualization, specifically a hypervisor, to pool those hardware resources together. But here is a golden rule you absolutely need to remember for your exams. Enterprise environments must use Type 1 bare metal hypervisors. Why? Well, unlike Type 2 hosted hypervisors that awkwardly sit on top of a clunky operating system, Type 1 runs directly on the hardware. We're talking near zero overhead, usually just 1 to 3%, and they can directly control the CPU's low power states to maximize efficiency.
Moving on to Section 2, Consolidation math. All right, this is the main event. We're going to run some real consultant-level calculations, because this is exactly where you'll rack up points on finals day. Get that scratch pad ready. Picture this. You're assessing an enterprise data center. You've got 80 legacy physical servers, and each one is drawing 150 watts. You step in, implement a virtualization project, and consolidate all those workloads down to just 8 modern host servers, each drawing 250 watts. I want you to hit pause right now. Run the numbers to find the total kilowatts saved, and let's see what you get. Got it? Let's break it down step by step. Step 1. Find your original power. 80 servers times 150 watts gives us 12,000 watts. Step 2. Find your new power. 8 new hosts times 250 watts equals 2,000 watts. Step 3. You simply subtract your new power from your old power.
And boom, the answer is a massive 10,000 watts, or 10 kilowatts saved. That is an 83.3% direct electrical production. And honestly, that's before we even start talking about the cooling energy you just saved.
Now, this is super important because server power draw is remarkably nonlinear. If you have 10 unconsolidated hosts sitting at just a 10% load, they pull about 1,400 watts because that idle power penalty is so high. But if you combine those 10 light workloads onto just 2 active hosts running at 50% load, your total power drops to an incredible 360 watts. You literally get a 74% reduction just by turning off the unused machines. All right, Section 3, Facility Math. Now that we've mastered the server level, let's scale things up and look at the broader facility impact. This is where power usage effectiveness, or PUE, comes into play. Here is your next scenario for the scratchpad. Say you've decommissioned 20 idle servers, saving exactly 3 kilowatts of IT power right there on the data center floor. The facility itself has a PUE of 1.5. Go ahead and pause the explainer again, calculate the total facility power reduction, and we'll check your work. Okay, the formula here is incredibly straightforward, but it's an absolutely vital concept. Your total facility power is simply your IT power multiplied by your PUE. So we literally just multiply our 3 kilowatts of IT power savings by our 1.5 PUE overhead factor. You should have landed on 4.5 kilowatts of total reduction. This is a beautiful thing to report to a client, by the way. It proves that every single watt you save at the server level magically saves an extra half watt in cooling and distribution overhead. The savings just multiply. Now let's turn that power metric into long-term energy, because that's how utility bills are actually calculated. If we optimize a cluster and save 15 continuous kilowatts over a standard 8,760-hour year, what's our total kilowatt-hour savings? Crunch those numbers real quick. To find this, the energy equation is just power multiplied by time. We take our continuous power reduction of 15 kilowatts, and we simply multiply by the total hours in the year, which is 8,760. And there it is, 131,400 kilowatt hours saved. To put that in perspective, if you factor that at 10 cents a kilowatt hour, you're looking at over 13 grand in impressive annual utility bill savings handed right back to the client, all from intelligent software consolidation.
Moving on to Section 4, Analytical Scenarios. Numbers are great and all, but exams and, real life are going to test how you actually apply this stuff. Let's look at how this hardware abstraction solves localized, real-world engineering constraints.
Imagine you're consulting for an enterprise data center over in Motijil, Dhaka. They're dealing with frequent 30-minute grid load shedding events, and it is absolutely destroying their UPS batteries by draining them way too deeply before the diesel generators can even take over. So how exactly does virtualization save their physical infrastructure in an emergency like this?
Well, it all comes down to the discharge rate. By consolidating workloads and literally slashing the continuous wattage draw on the floor in half, you effectively lower the battery discharge rate. This instantly doubles your UPS backup runtime. It stops the rapid degradation of those batteries and buys the diesel generators plenty of time to spool up and stabilize the load safely without dropping any critical banking systems.
All right, Section 5, Concept Quiz. You've nailed the math and you've got the practical applications down. To round out this explainer, let's test your core theoretical knowledge with a rapid-fire quiz. Let's see if you can articulate the why behind the numbers.
Question 1. Think back to that power curve we looked at earlier. Why exactly is a physical server running at only 10% capacity such a massive disaster for green computing? It is entirely because of idle power overhead. A server doesn't just magically scale its power down to 10% because its CPU is at 10%. In reality, 50 to 70% of its maximum power is drawn continuously, even when it's doing absolutely zero active processing. That baseline power is just sitting there maintaining the memory, the motherboard, and the network cards.
Okay, last question for your finals prep. Automated tools like distributed power management are fantastic because they shift virtual machines around to save power. But why must we program threshold hysteresis, which is basically a delay or a buffer, into our live migration algorithms?
Because migrating a virtual machine is not free. It heavily costs network bandwidth and CPU energy to transfer that memory state. If your algorithm is too sensitive and it's constantly bouncing machines back and forth, you actually create a net energy loss. Which leaves us with the ultimate question you should always be asking yourself as a green IT consultant. Is your automated data center actually saving energy, or are you just burning power to shuffle it around? Keep that in mind as you head into your exams. Good luck, and I'll catch you in the next explainer.